Now that we're done discussing some of the small molecules and some of the fundamentals of structure that you learned in general chemistry, let's move on to a new topic, and that of representation of molecules and the drawing of them. In general chemistry, you learned, of course, about the molecular formula, which does explain to you how many of each atom type is in the molecule. But in organic chemistry, we're going to be dealing a lot with interactions of different molecules with other reagents, and we need to be able to find locations on the molecule. But at the same time, drawing a Lewis structure can be quite difficult, or at least drawn out, and you don't want to take the time, and it can be quite complex. So there is, of course, as you've read in your reading, the condensed way, which kind of shrinks down the Lewis structure like this, into saying, well, let's not draw all the H's, all the bonds of the hydrogen to carbon out. We'll just say CH3 and just understand that those three hydrogens are connected to the carbon. And then next to that is the carbon that has the H attached to it. And then there's the OH, which is right here. Now, what about this CH3? Well, you may have noticed that there's a little 2 right there, which is explaining that there are 2 structures that look like CH3. Surrounding the CH and the OH and how they're connected. Now, you can do the same thing for propanol and ethyl methyl ether. And so let's go ahead and see if you can draw those. Now that we've practiced some of the simple ways of representing molecules, they're still not quite enough because they still shrink it down too far and don't allow us to see the structure of the molecule. Take, for example, amoxicillin. There's a lot of interesting functional activity that's important with amoxicillin, how it will behave, that's based on the locations of the different atoms. And so we still need to see that. And so, but to draw the Lewis structure, if you see it right here, you just have to draw those hydrogens out and the carbons, and you're just doing stuff over and over again. So chemists have come up with a much easier way of drawing it, and that's what's known as the Bondline structure. And really, the bondline structure is quite straightforward. It's the idea that you already know that these molecules are chains of carbons connected together. And so we just need a way to kind of know or indicate to our colleagues in chemistry where those carbons are. And also, we already know that the hydrogens are following the octet rule, and the carbon is too. And generally speaking, we just know how many hydrogens there are. And that's what happens here. We drop off the hydrogen in the carbon symbol because we know right here that this vertice is a carbon, and that the lines are the bonds that that carbon has to its neighboring carbons. And take, for example, this one right here. The fact that it only has 1, 2, 3 lines surrounding that vertice must mean that it has one hydrogen on it that's just not being shown, because it needs to have 4 bonds to it. Unless it's charged, but we'll deal with that later, more likely in lecture. So let's just take a look at a quick way to kind of be able to read a bondline structure when you're given it, so if you're already given it. And that is, wherever there's a vertice, or an endpoint, so it's also at the very end where the line comes to an end, those are carbon atoms. And the lines are the bonding that is existing between the carbon atoms. Now, one thing to notice, you still draw any non-carbon atom or hydrogen out, so the oxygen's still drawn. When we look at this bondline formula, we know that this right here is a vertice, so it's a carbon. This must be a carbon. This must be a carbon. And then these endpoints are carbons. They come to an end at a carbon. That's oftentimes what students maybe forget it. And then look at this carbon. It only has 1 bond to it, so it must have 3 hydrogens. Look at this carbon. It already has 4 bonds to it, so it has no hydrogens, and so forth. So the hydrogens are understood because we know the rule, unless the carbon atom is charged, it must have 4 bonds, which is equivalent to 8 electrons, the happy octet. So that's how we know where the hydrogens are located at. So you just have to practice that, just draw some bond lines or find them online, and just try to figure out if you can see and visualize where all the carbons are, and then where all the hydrogens are at. So now let's talk about drawing a bondline structure. So you got a Lewis structure right here, and you want to draw the bondline structure. So first of all, the Lewis structure is usually given at least with no sense of geometry of the molecule. And we know that these carbons are tetrahedral, so we know they should have a zigzag shape. So that's a common thing you'll find, is that you need to have a zigzag shape in your structure. Another thing is you don't want the bonds to be angled in a way they don't make any sense. And so in this structure right here, this carbon is sp2, and so it should be trigonal planar, and it should have them pointing 120 degrees from each other. But if you have the oxygen pointed down here, that's just not the real geometry of this carbon atom right here. It's going to be pointed. The oxygen isn't going to be pointed here between these like this, where I don't even know what angle that would be. No, instead, it's located in a way where you've got 120 degrees between the two bonds. Now, that's for double bonds because that's when the carbon would be sp2 and have trigonal planar geometry. For single bonds, because they're typically connected or let's just say when you've got some single bonds that are connected to an sp3 carbon, so there's no double bond anywhere on that carbon, then generally speaking, you can orient those bonds in any geometry, relatively speaking, or at least you can put them in different ones and still be accurate. So these two structures here are both valid. This is wrong because you're violating the geometry we expect for this carbon. This one's okay because all you're saying is that in this one, what's located in this position is a hydrogen. Now the carbon's down there, and the hydrogen is up here. And if you were to build your model kit, and we'll look more at this when we talk about conformational structures and the different conformations molecules can have, that's just rotating the bonds. You're not changing the structure, it's still the same structure, and it's valid because you can easily rotate the bonds around. The fourth rule is you still draw heteroatoms. And if they have hydrogens connected to them, you draw those too. And the last one, it's a very important one, and it's where students oftentimes mess up and lose credit for their structures, and even mess up their chemistry and their reactivity and product outcomes, because they just don't think about this. Never put more than 4 bonds to carbon. Never put more than 4 bonds. It isn't, and really you should never put more than 8 electrons around any period 2 atom. So nitrogen, oxygen, they all can never go beyond 8 electrons, nor carbon. That's why carbon can never have more than 4 bonds, because 4 bonds would be 8 electrons. A 5th one would be 10 electrons. So let's take a look at an example of drawing or figuring out the bondline formula from a Lewis structure. So we start with this Lewis structure here. And you don't have to go through this whole process. I just wanted to walk you through the visualization of slowly condensing it down into the bondline structure. So first of all, we're going to get rid of the hydrogens. Let's go ahead and make it in what's oftentimes called a semicondensed. And this is the way you can draw these molecules when you're just drawing them on your own and trying to solve other problems later on in the semester, such as chemical reactions and product outcomes, and just generally drawing structures for me. I don't always hold you to a complete, pure bondline structure. I usually am okay if you want to throw in semi-condensed. So this is the structure as we condense down all the hydrogen bonds to the carbon, to the oxygen, etc. We've transformed them into just these symbols next to the atoms that they're connected to. You know, H3 meaning 3 hydrogens are connected to this carbon, H2, 2 hydrogens are connected to this carbon. You can call this a semi-condensed. It's perfectly valid if you're not being told specifically to draw a bondline structure, such as later on in the course when you just want to draw a molecule as a product or just a structure in general. But if you want a true bondline, we need to take it a little bit further. And so the next step is to just remove all hydrogens, except any hydrogens that are connected to a heteroatom. So anything that's not carbon. If it has a hydrogen connected to it, you leave it in the structure, but you still keep it condensed down. Connected to the heteroatom like that. And then lastly, you get rid of the carbons and turn them into those vertices like that. So that is the bondline formula for the molecule that we started with as a Lewis structure. Now, as we'll talk more about in lecture, you can leave off the lone pairs because we will know whether or not lone pairs are present based on the presence of formal charges. That's generally the expectation. You'll never have me, at least, give you a molecule where I give you neither the formal charges nor the lone pairs, because at that point you have not enough information to determine anything. So you have to be certain that whatever you're given is showing you one of those two things, either all the lone pairs or all the correct formal charges. Something has to be presumed about that knowledge. So let's go ahead and have you draw, or at least tell me, what is the correct bond line structure of this molecule. So here we have a series of examples of common functional groups. Now the previous slide showed you an alkene, which is carbon that's double bonded to another carbon. We also see here an alkyne, which is a carbon triple bonded to a carbon. These I don't typically have you point out as functional groups in functional group problems. Also, I don't have you point out typically the aromatic or arenes, although you should be familiar with this terminology. However, you likely get familiar with this terminology because we will talk about these types of bonding often as we begin to study those molecules, alkenes, alkynes, and aromatics throughout the course this semester and next. But particularly I wanted to focus on functional groups that oftentimes have a major role in chemistry and oftentimes involve heteroatoms. For example, alcohol is a molecule that has an OH connected to one of the carbons. That's an alcohol. An ether is a molecule that has an oxygen that is sort of inserted between two carbons in a carbon chain, such as here in diethyl ether. Now, thiols and sulfides are essentially analogs of the alcohol and ether, where instead of an oxygen, there's a sulfur there. I'm not going to have you point out thiols and sulfides as problems, but you should still become familiar with this terminology. And then two more functional groups is known as aldehydes and ketones. And this is where you've got a C double bond O called a carbonyl connected to an R group and connected to an H group. And that's an aldehyde. And then the ketone is where you have a C double bond O connected to two R groups. By the way, R group is just another way of saying some chain of carbons. It could be a CH3, it could be something larger. It's just something, it's initially connected to a carbon. That's what this R means. There's at least one carbon here, and then a bunch of other stuff possibly. Could just be 3 hydrogens, could be a bunch of other stuff. And so that's how you recognize an aldehyde and a ketone, is it's got one carbon connected, some chain of carbons connected to this carbon with a double bond O and a hydrogen, and then you've got a chain of carbons connected to this carbon, connected to a double bond O, followed by another chain of carbons. Could be just a CH3. Here we see two examples of an aldehyde and a ketone. On the left-hand side is the aldehyde, right-hand side ketone. What differentiates these two functional groups is in an aldehyde, one of the two connections to the carbon that has the double bond O on it is a hydrogen, whereas the other one is either another hydrogen or a chain of carbons. Whereas in a ketone, those two groups that are connected to the carbon that's double bonded to an oxygen are both some type of chain of carbons. Could be a CH3 or longer. Some more carbonyl compounds that you should be familiar with are the carboxylic acid, in which you've got a C double bond O and an OH connected to a chain of carbons. The acyl halide, where you have a C double bond O connected to a halogen at the end of a chain of carbons. You've got the anhydride, or acid anhydride it's sometimes called, in which you have a carbonyl C double bond O connected to an oxygen, connected to another C double bond O with a chain of carbons after it. You have the ester, in which it looks essentially like a carboxylic acid, but instead of a hydrogen here, there's a chain of carbons. And then the amide, in which you have a C double bond O with a nitrogen on it. No, that nitrogen could, these R's right here could be hydrogens, or they could be chains of carbons. And then finally an amine, in which you have a nitrogen that has some combinations of hydrogens and carbon chains connected to it. 3 of them, at least 3 of them. That's what's an amine. So there's 3 single bonded groups coming off of this nitrogen, and they could be a carbon chain or they could be a hydrogen, and it could be any combination. We'll learn more about those next semester, but you should still recognize when you see an example such as this diethylamine, you should recognize that this is an amine because it's a nitrogen connected to three things that's a hydrogen and some carbon chains. So those are the functional groups, and we'll discuss more of this in class.